So hello and welcome to our seminar today. And today our speaker is Benjamin, who couldn't travel to Chennai for the conference. And so it is nice that he's going to speak here instead, online. And he will tell us about nonlinear response in real-time holography.
Okay, so yeah, thank you very much for giving me this opportunity to talk virtually. It's a shame that I could not attend in person. Yeah, so this is some recent work I did with Christiana Pantelidou on essentially computing 3-point functions in real-time holography. So the archive number is there. It was released towards the end of last year. Okay, so we're interested in this retarded correlation functions, retarded response of strongly coupled quantum field theories. And we're going to be thinking about finite temperature. So the most obvious observable in this class of observables is the retarded 2-point function. So here I've written down what is the retarded 2-point function in a relativistic quantum field theory. You have some operators, let's call them O, and then we insert them in x1, x2, we take the commutator and evaluate the expectation value of this in the thermal state. And then we have this theta function. So the support of this retarded 2-point function we're calling GRA for reasons that will become clear shortly. And it depends on these two insertion points, x1 and x2. And we can think about the support of this function as follows. So if we place our insertion at x2, then it has support provided x1 is in this future light cone. And that's because if we move x1 into this space-like separated regions, then this commutator guarantees that we get a 0. And if we move it into the past light cone, then this theta function will give us a 0. So it's only supported for x1 in the future. And if we want to compute this object, we're going to need some notion of real-time holography, since it depends crucially on the time ordering. And this is intrinsically not a Euclidean object, it's a Lorentzian object. But this gives us a bit of a challenge, because the usual sort of way that we think about the ADS-CFT dictionary, or this GKPW dictionary, is between partition function of our quantum field theory and some path integral in some string theory path integral in the bulk, which we approximate with our gravitational saddle point. And we have our sources in the quantum field theory, and this translates into boundary conditions for the fields in our gravitational path integral. So if we think about ADS soup can picture, we have our boundary conditions on our fields in ADS-CFT given by these sources J on the boundary. Whilst this is well suited to a Euclidean problem, since if on the boundary I specify all of these sources, I can construct locally unique solutions to the gravitational path and the gravitational equations of motion. It's a Euclidean problem, and that specifying the sources at the boundary is a well-posed thing to do. In the Lorentzian, it's no longer the case, since in order to construct this Lorentzian solution, we need not only boundary values, but also some initial data or maybe final data. And this corresponds to a choice of state in the quantum field theory. So this typical GKPW-like dictionary applied in this real-time context is not sufficient to completely fix which observable we're computing, since we would need to know what is this initial data. So the relationship between these two things is clearly, if I want to compute this 2-point function, I would consider it's a linear response calculation. I could think about the Klein-Gordon equation in the bulk. One of the boundary conditions for my Klein-Gordon field is fixed by the sources J, and then the question is, how do you fix the remaining piece of the Klein-Gordon solution? And that's related to this choice of initial data. Okay, but historically, this has not been a problem. This did not present an obstacle for computing this 2-point function, this retarded 2-point function, since people came up with a clever prescription in the bulk, which gives you the right answer. So when you take your Klein-Gordon field and you solve it with the boundary conditions given by the sources that you want, the additional condition you need is an ingoing boundary condition at the future event, at the event horizon of your black hole spacetime, describing the thermal state. So equivalently, this corresponds to a regularity condition at the future event horizon. So we think about our Klein-Gordon fluctuations. we have the sources at the boundary, and an ingoing boundary condition at the horizon. So we have a mixture of things going on. We have a boundary condition from the asymptotic boundary of ADS, and we have some other condition coming from the interior. This is the sort of Son-Starinet's prescription for computing these retarded two-point functions in a thermal state. And what they found is when they do this, you find that these objects will have, in momentum space, will have simple poles, and those simple poles correspond to the quasi-null modes of this black hole. So it's a very beautiful result, the connection of these two-point functions in quantum field theory and these quasi-normal mode values. But as I've been hinting, this is sort of unsatisfactory from an ADS-CFT point of view, from a boundary perspective, since this prescription is a mixture of things which live at the boundary, where you pick your sources, and something which lives in the interior at the horizon. So the question is, how would you impose this ingoing condition from a CFT point of view? And this has been resolved a bit later by using a real-time holographic prescription. And I'll go into detail how you do this in a few slides' time. But if there's a way of extending this GKPW dictionary to real-time situations, one of the ways of doing that is this Skanderis-Van Ries real-time holographic dictionary. And within that dictionary, it's possible to derive this ingoing boundary condition purely from things you specify at the boundary from a CFT point of view. So we'll get into that shortly. So in this talk, what we're interested in is extending this from 2 points to 3 points. So we'll consider, let's say, scalar fields with a bulk interaction term. And then the natural object to consider is a retarded 3-point function. So the natural object is this one. So instead of just a single commutator at 2 different points, you have 3 points and this nested commutator. And then you have 2 theta functions, which say that 1 has to be the future of 2, 2 has to be the future of 3, and then you add in the swapping the points 2 and 3. So you don't care about the ordering of 2 and 3, but you just care that 1 is to the future of both of them. So in other words, this function, this sort of fully retarded 3-point function, has support in the following configuration, when we have x2 in the future light cone from x3 and x1 in the future light cone from x2, or if we consider the analogous diagram, but where we swap 2 and 3. So computing this is no longer a case of doing a linear response problem like a Klein-Gordon equation on a fixed black hole background in the bulk. It's now a nonlinear problem. We need these 3-point functions. So we're going to consider some interactions in the bulk. And it's not obvious that we can use these sort of ingoing prescriptions that were given to us for the 2-point function case, these Son-Starinets or Herzog-Son kind of prescription. And so we want to start from scratch using a real-time holographic formalism. We use the Skanderis-Van Ries formalism, and we'll derive these 3-point functions from those from first principles using these formalisms.
So, sorry, I have a naive question. Is it a good time to ask?
Yes, please do interrupt. Yes.
Yeah. So suppose are we also going to use ADS CFT? Like, are we the boundary is a CFT?
Yes. So in everything I've said so far, I think is not specific to CFTs.
Yeah, but like,
however, in this talk, yes.
Yeah, for a CFT, just by using symmetries, won't I be able to fix, like, let's say x1, x2, x3 to a particular point that I'm interested in, and
so you have only translations and boosts, I suppose. So you can fix, let's say, the position of one of these points, but because it's at finite temperature, most of the
sorry, it's a finite temperature, so you will not have the
exactly.
Sorry, okay.
No, thanks for the question. I should clarify that. Everything I'm talking about is thermal physics. We're thinking about these black holes in the bulk, and we're computing these retarded correlation functions in those thermal states described by those black holes. Exactly.
Okay, thank you.
Thank you.
I have a question. So, so when you say you can't use Son-Steinitz or Herzog-Son, I mean, is it for the philosophical point of view you mentioned, or, I mean, their computation of a 2-point function, can it be applied for 3-point functions as well?
So we will see, indeed. So mostly it's a philosophical objection, and we're going to start from this real-time prescription. That's the perspective. However, what we'll find is something that looks very similar to Son-Starinets for 3 points. So when you look at 3 points, we'll do perturbation theory in the amplitude of our bulk field, obviously. So leading order will have some linear response calculation. That linear response calculation will have ingoing boundary conditions. And then the question is, what do we do for the nonlinear correction to that, which depends on this 3-point coupling? And by using this real-time prescription, we'll find that there's an analogous sort of ingoing condition for that nonlinear perturbation as well. So it does turn out to be very similar in spirit to Son and Starinets, but we wanted to get there without assuming that.
Okay, thanks.
Ben, so
Yes.
yeah, I mean, so what you said probably answers the question that I'm going to ask, but this is actually a causal response as well, but it's a nonlinear causal response. So you would expect that it's given by a general, I mean, it should be given by ingoing boundary conditions after all. But of course, you have to implement the ingoing boundary conditions simply at a nonlinear level, right? That's all.
Exactly, yes. So one should not be surprised that that's what we found. Indeed, we're talking about causal response, nonlinear causal response. So having something that's only ingoing at the horizon is what you might expect to happen, but we get there sort of more formally from this real-time approach.
So you're trying to show that the real-time approach of Skenderes, Balvan that also reproduces the causal response at the nonlinear level, not only a linear level.
Exactly, that's right. Yeah. So that's the first thing. That's the first exercise we're going to do in this talk, and then after that, we'll do. Once we've shown that, we'll do a numerical computation of these 3-point functions and show you where the similarities are.
So I have one more, just one more small clarification. So for 2-point function, we know using Kubo formula, one can relate it to the transport coefficient, or quasi-normal modes also are related to the poles.
Yes.
For 3-point function, do I have such features?
We don't. Okay, so in terms of Kubo, we don't have anything analogous to that at this point. However, what we do have is a relationship between the singularities of the 3-point functions and quasi-normal modes, and we'll go into that in some detail in a few slides.
Okay.
So this is one of the motivations. If I carry on, I'll get to a list of motivations, and this will appear as one of those. Oh yes, this next slide. Okay. So why are we doing this? Well, one reason is, in principle, we have ADS-CFT, which is immensely powerful in the sense that we can use it to study strongly coupled systems non-perturbatively and in real time. And I think that this real-time formalism has not been used to its fullest extent, and one of our motivations was to sort of make progress in that direction by computing new things using real-time holography. That was one of the motivations. This question that was just asked, exactly. So in 2-point functions, we saw, sorry, was there a question? No. So in 2-point functions, we saw Son, Starinets, and co. saw that the quasi-normal modes appeared in these 2-point function response in and that's an important connection between sort of black hole physics and strongly coupled field theories at finite temperature. The question is, does that continue to higher points? Does that sort of universality of black hole ring down appear in higher point functions in quantum field theories? So what is the analytic structure of these 3-point functions? And do quasi-normal modes appear? So this is one of our motivations. Again, related to the previous questions, is there a simpler sort of ingoing proxy type computation a la Son Starinets for 3 and higher point functions? And we'll see that there is. And another motivation that we had was, well, one of the topics that people study in terms of gravitational waves and waveform fitting is nonlinearities of ring down in black holes. So in asymptotically flat contexts, obviously there's the longest lived quasi-normal mode of Kerr, and then if you try and fit the waveforms of gravitational waves in the ring down phase to just a single quasi-normal mode, it doesn't work very well. So what people do is either add the higher overtone modes, and then also it would be natural to add the nonlinearities, since they would presumably have a similar time dependence as the overtones. So there's a topic, sort of ongoing work in in that area about computing nonlinearities for these ring downs. And in my view, at least in the ADS context, the quantum field theory sort of systematizes the treatment of those nonlinearities. Since we know all of these leading nonlinearities will be captured by 3-point functions and then 4-point functions and so on. So I think the structure of quantum field theory, which organizes the nonlinear computations in ADS-CFT, may or may not be useful for thinking about these asymptotically flat problems that people face in waveform fitting. I don't have anything direct to say about that, but that's just sort of one of the tangential motivations for this work. And appearing almost simultaneously with our work was this paper by Loganaga, Rangamani, and Pirueta, and they had some related calculations, I think, using a slightly different real-time formalism, and it'd be interesting to see if everything's lining up appropriately. Okay, so the plan is first talk about Schwinger-Keldysh contours and how we could do real-time response in quantum field theory.
Upload कर दिया था.
Was there a question, or I think there was maybe background noise? I'm not sure. And the second part of the talk is this review of this deriving this Sonsdauer-Netz ingoing prescription from a real-time 2-point function calculation, trying to do an analogous thing for 3-point functions, and then showing you the numerical results for some 3-point functions of scalar operators in ADS5 CFT4. And if time permits, I will also like to discuss analytic properties of these retarded correlation functions in momentum space and what that means, but in terms of transport and hydrodynamics. And as, yes, please do interrupt at any point if there are any questions. So let's talk about Schwinger-Keldysh. So the basic, what we need to do in order to do real-time holography is to write down a generating function for these retarded 2 and 3 and so on point functions at finite temperature. So we had, remember, this 2-point function, which was this commutator with the theta function. So the question is, how do you write down to the path integral with sources such that when I vary it, I get this object with the appropriate commutator and the theta function. So the way this is phrased is as part of a larger matrix of correlation functions. Instead of just GRA, which is this commutator, it's actually a 2-by-2 matrix of response, linear response. We have GRA, which is the one we've talked about, but then there's, that's the retarded response. And then opposite that is advanced response, so GAR. So it's still a commutator, but now the theta function is, we swapped 1 and 2. So 1 is to the past of 2. There's another entry, GRR, which is a sort of symmetric piece, and this is the anti-commutator of those 2 observables, 2 operators. And there's a 4th piece, which is identically 0. These retarded and advanced pieces are related to each other essentially by time reversal or complex conjugation. And the symmetric piece is related to these retarded and advanced pieces by a fluctuation dissipation theorem. So really, in this case, there's only one independent correlation function, and the rest of them follow once you know it. So once you know GRA, you can write down GAR, and then you can write down GRR using fluctuation dissipation, and GAA is 0. This is at the level of 2-point functions, and then at 3-point functions, there's a 3-by-3 matrix, and there are associated fluctuation dissipation theorems, generalized fluctuation dissipation theorems for those higher point correlation functions. So to get at this generating function, what we're doing is we're embedding this retarded response in a more general framework of all the different types of response that we can have.
So I have just one naive question. So can you go to previous like this? I could have done the calculation all in Euclidean space and then appropriately analytically continue to get all the 4, right? Is that a possibility?
I think that is correct, yes.
So in that, so I'm just curious. So for a higher point function also that can be done. So is there any advantage to actually do it through real-time formalism? Just a curiosity, I'm just trying to understand.
Well, I off the top of my head, I don't know how one would do the analytic continuation in this context, in the sense that what we're going to do is we're going to, at a given, ultimately we're going to be looking in momentum space, and for a given, let's say, set of momenta, we're going to solve the bulk equations numerically, and then we'll read off the response function. So if we were to do this in the Euclidean, I'm not sure how the analytic continuation would work on a practical level for computing these objects. If you didn't have analytic control over the function you're computing, you're just doing it numerically, I don't know if that's going to be easier than what we're doing here. I think you're right that it is possible to do a Euclidean computation and by carefully analytically continue and get to these objects, but I'm not sure that it's more practical.
I see. Because you're saying you don't know the analytic structure, you are just doing numerically the calculation. So
yeah, so even at the 2-point function level, as long if you're in ADS4 and above, then it's numerical.
I see.
And so I'm not sure to what extent one can do the analytic continuation.
Okay.
And I think it's nice. Okay, so there's that practical aspect, and I think it's nice also to directly work with the things in a real-time setting. If you're computing real-time observables, maybe you see things that you would not have seen from the Euclidean point of view. Yeah, so just a conceptual viewpoint as well.
Even if you manage to somehow interpolate and get this Euclidean propagator, Euclidean in G omega, is when you do analytic continuation is typically very unstable numerically, because you can the two different Euclidean correlations, which are very slight differences, can have vast differences in real time, even in the real rest. So it's very numerically extremely unstable or it requires exponential precision in order to get to do the analytic continuation correctly. It's very costly exercise, even if you are managed to do it numerically.
I see. Yes, that sounds, yes. I mean, this is something I've not tried to do, but it does sound. What we're doing here ultimately will be very easy, and so I think this is a very practical approach. What we're doing. Okay, thanks again for the questions. So to get this generating function, we consider this Schwinger-Keldysh complex time contour. So instead of considering our quantum field theory or conformal field theory just in Lorentzian time or just in Euclidean time, we consider it as living on in the same space, but on this complexified closed time contour. So there's a Lorentzian piece, which I've drawn here in blue, which we'll label as 1. So the Lorentzian piece will go forward in time, then we'll attach it to a Lorentzian piece that goes backwards in time, which we'll call segment 2. And then there's a Euclidean piece, which will have time coordinate tau, and the period of this Euclidean piece is beta. So we'll periodically identify the origin with -I beta. So this is a thermal circle of radius beta, so this corresponds to the inverse temperature 1 over beta. And we can see that because time evolution in this Euclidean direction corresponds to this, inserting this e to the minus beta h density matrix. So this Euclidean time circle prepares our initial thermal state, and then we go forward in time and we'll have some sources or insertions on these Lorentzian pieces, and these sources and insertions will compute our correlation functions. So when we insert our operators or turn on sources, they will be labeled by where we insert them in this contour. So they'll either appear on this segment 1 or on segment 2, and so we'll label them by operator that lives on 1 or operator that lives on 2, or source that lives on 1 or source that lives on 2. So the idea is now that if we consider our quantum field theory path integral, where our quantum field theory lives on this complex time contour in the presence of these sources, this path integral will generate contour ordered correlation functions. So let me be a little bit more specific. If instead of using sources label and operators labeled by 1 and 2, we switch to a slightly different basis. So here I'm taking the difference between the sources 1 and 2, let's call that JA, and the difference between the operators, call that OA. And then the average of the sources, which we'll call JR, and the average of the operators, which we'll call OR. So this is just a slight rotation in our basis. Then this path integral becomes a function of JA and functional of JA and JR. And it's given as follows. So we have this contour ordering operator, TP, and we have the insertion of this exponentiated JA, OR, JR, OA. And this is all in the thermal state. So by taking appropriate variations of this path integral, this J with respect to JA and JR, the claim is that we will generate all of these matrix of response functions. Let's just look at that. So we take this path integral living on this complex time contour, and we take variations with respect to these sources and set the sources to 0. This generates all of these retarded and advanced and everything else in between correlation functions. So just as a check, if you were to take this path integral with this contour ordering operator and you vary with respect to these sources, you can show that, if you want GRA, you would take a variation of this path integral with respect to JA and JR, and you would get, by considering the contour ordering and after some tedious calculation, you would get indeed this anti-commutator, with the theta function. And similarly, if you took the 3-point function, you take 3 variations of this path integral with respect to the appropriate sources, and you would check after a tedious calculation, indeed, you get this nested commutator. So that this claim is indeed the case that if we have this contour ordered path integral with these insertions, then this serves as a generating function for the retarded, in particular, serves as a generating function for the retarded correlation functions that we're interested in, as well as everything else that we're not going to compute, like the advanced and the fluctuations, the symmetric piece, and so on. So the reason we did this, of course, is now we want to get this, we want to get these retarded correlation functions from a variation of the path integral, and we know, and this is where ADS-CFT steps in. The ADS-CFT will tell us what this path integral in the presence of sources is from a gravity computation. So in particular, in the Euclidean context, that's just the GKPW dictionary. But in this real-time context, we need to replace the quantum field theory path integral with our gravitational path integral, where we have an appropriate dual to this complex time contour, this Schwinger-Keldysh contour. So this is, in essence, the Skanderis-Van-Ries prescription. We think about all the saddle points of our gravitational path integral in the bulk, whose asymptotics become this complexified time path, this Schwinger-Keldysh contour on the boundary. So we're looking for bulk geometries for which this complex time path is the boundary geometry. And one way we can do that in this current context is to fill in the bulk using piecewise smooth fields. So for instance, we have this Lorentzian piece of the contour in blue, labeled with time t1. This we can fill in the bulk with a copy of the Lorentzian black hole, let's say Schwarzschild. That's denoting this piece of this diagram on the right-hand side. The green piece is another Lorentzian piece, but time runs backwards. So we can do the same thing. Again, a piece of Schwarzschild with the time coordinate reversed. And for this Euclidean time circle with period beta, we simply take the Euclidean Schwarzschild solution, so this Euclidean Stegar, the black hole Stegar solution, and then we want to make sure that we join all of these pieces together in a way that solves the Einstein equations. And the way we do that is by ensuring that everything is C1 continuous, C1 smooth across these gluing surfaces. So we have this piecewise solution a Euclidean Schwarzschild and two Lorentzian pieces of Schwarzschild, and we glue them together. So this Euclidean cigar geometry is, you take the full disk and then you cut out a wedge. You take a cut, let's say at tau equals 0. Usually you would identify tau equals 0 with tau equals beta, so that imagine you cut the disk open along that line. And that's this black cut that I've drawn in here. And then in that cut, you would attach these Lorentzian segments in a way that's smooth C1 at these joins, denoted by these dashed lines. And then in the Lorentzian, you would, at some late time surface, or however late you need it to be for your insertions and your sources, you would glue the two Lorentzian pieces together, again, along this dashed line. So this is just a way of constructing a solution to the Einstein equations, and therefore a saddle point for our gravitational path integral, where the boundary is this Schwinger-Keldysh contour. All right, so with this prescription in mind, we can now return to this statement that the Son-Stauronet-Zaingoing prescription can be derived from this real-time formalism. So I'm going to review this argument. This was presented in a paper by Van Ries. So what we're wanting to compute is this retarded two-point function GRA. So remember, we need to compute the gravitational path integral in the presence of these sources, which live on these segments 1 and 2, and take appropriate variations to get GRA. So it's a linear response calculation since we're doing two-point functions. And so we just need to consider the Klein-Gordon equation propagating on this piecewise geometry, which we'll call G bar, which was comprised of Lorentzian pieces and Euclidean pieces of the Schwarzschild black hole. So we'll denote our Klein-Gordon field by psi, and we'll label it by which segment this piece of psi lives on. So it's a piecewise geometry, we're going to have a piecewise solution to our Klein-Gordon equation. So we'll have psi 1, which lives on Lorentzian 1, psi 2, Lorentzian 2, and psi e, which lives on the Euclidean disk. And then we have the box operator, which lives on this geometry G, again labeled by whichever piece you're looking at, 1, 2, or the Euclidean. We have to solve this equation. We have to solve it subject to the boundary conditions that there is no sources in the Euclidean at all. Since our generating function, we didn't have any sources on the Euclidean, we just had sources J, R, and JA, which correspond to a mixture of J1 and J2. So we need, on the boundaries of these Lorentzian pieces, the ADS boundaries of these Lorentzian pieces, these blue and these green lines, we need to have sources for this, boundary values for these bulk fields given by J1 and J2, corresponding to the source behavior near the boundary. And then we need to make sure that we solve this equation in a piecewise fashion at the joins themselves. So we need to make sure that we've glued appropriately across these junctions between the Lorentzian and Euclidean pieces and between the two Lorentzian pieces. So there are appropriate matching conditions on these Klein-Gordon fields you can derive based on those gluing C1 continuity conditions. So this constitutes a boundary value problem, since we have a field and some boundary values. At no point do we have a condition, let's say, of ingoing at a horizon. So that's something which we will see that emerges. So you can see everything is essentially up to this condition that we've solved the Einstein equations, which is the matching condition. Everything is prescribed at the boundary, so it's appropriate from a CFT point of view. So how do we construct
Sorry, just one question. So here, for example, you are also dealing with time-like infinities, right? So you put some boundary condition there as well?
Time-like infinity. So we're bounded. So let's see. So on this contour, we'll go up to some final value. Let's call it.
I mean, so when you're taking this Lorentzian segments, this T1, T2 lines.
Yes.
So it goes all the way. So suppose you're cutting it at T equal to 0, which coincides with tau equal to 0, but now it's going all the way up, right?
No, we go up to some maximum value. Let's call it some finite value, TF, let's say. So the horizon would be to the future of this gluing surface. So we don't need to ever get to the horizon itself.
I mean, this T1 runs from 0 to some finite value. There is no time like infinity or
so we run it. So we can take it to be any, we can run it to any value we like. And at that value, we just glue it onto T2. So we can do that at any value of time. The only condition is that, of course, if we want to insert sources on these contours, that they, our time has to extend past any insertions. So we just make it as late as it needs to be to be after any insertions. So for instance, if we have no insertions at all, then this final time could be 0, and we would just end up with purely the Euclidean disk with no Lorentzian pieces at all.
I mean, if I recall Skender's paper, I think he has some argument like, so near the infinities of near the Lorentzian time like infinities, they are probably capping off the geometry and again further gluing by a Euclidean segment to get rid of the time like divergences. I mean, is that
yeah, that's okay. So that would be a computation. So in their papers, they not only considered thermal correlation functions, but also sort of in-out computations. So if you imagine you prepare a state and you do some computations, then you have a final cap. You have an initial Euclidean cap and a final Euclidean cap and the Lorentzian evolution in between. So in that context, yeah, that's a different complex time contour to the one we're considering. And that would be a very different bulk geometry associated to that. So that would be a Lorentzian evolution with 2 Euclidean caps. Maybe that's what you're referring to. So here what we need to do is we go up to a certain finite time, then we go back, and then we go around the Euclidean circle. And so we have a closed contour in that sense. So we can run around this contour and we just get back to where we started. So there is a final time. It's not infinite. It only needs to be as large as the latest insertion we have. And if there are no insertions in the Lorentzian, it can be 0, and then we just have a purely Euclidean calculation.
Yeah, and yeah, so that's fine. And another complication is this, like this corner divergence that he talks of, and I understand that is like a state dependent thing because you have to check geometry wise that if such corner divergences are present for the fields. For example, when these Euclidean segments are matching with this Lorentzian.
So here, yes, so here this would correspond to, you can think about it in a couple of ways. One of them is you need to have, I mean, essentially you just need to have a solution of the Einstein equations so that you have a saddle point of your path integral. And the minimum condition you need is that the fields are continuous at these joins, and the derivatives, the first derivatives, are appropriately continuous. So you would take, so here, this Euclidean to Lorentzian join, you would have a tau derivative would have to match a t derivative of this field with an appropriate factor of I to account for the fact that it's a 90-degree corner. These conditions are all worked out in these papers, and they derive them from essentially stationarity of the action. So there is, but it boils down to really this continuity condition, ensuring that you've solved the field equations in the bulk and therefore have a saddle point geometry.
Okay.
One could imagine doing other things like having a completely smooth geometry that would be more, intrinsically complex. So here, whilst the signature has changed, so this is the Euclidean signature, these are Lorentzian signatures, the metric components are real. One could imagine thinking about complex geometries which fill in this contour, and I think that's an interesting question, but I don't think that's been considered. But what we know for sure is that when we impose these C1 conditions, we'll have a saddle, and that's all we need. So this is just a way of, this piecewise smooth plus these C1 joins is a way of constructing solutions to the bulk equations of motion. I don't know if that answered your question, hopefully.
No, that's fine. I mean, we can. Right.
Okay, thanks. Yes, we have this boundary value problem. How do we solve that in practice? So the way to think about this is with a set of bulk to boundary propagators. So imagine we turn on a source, a delta function source, on one of these Lorentzian pieces. Let's do it on this green segment 2. We have the star here, which denotes the delta function source. So this will excite some modes in the bulk for the scalar field. Some of these will be going forwards and some of these will be going backwards. And then these will propagate through the geometry. So they'll propagate across the gluing surfaces by demanding this is a solution. There'll be support in the Euclidean, support in the Lorentzian on both segments, since this field will influence through the gluing conditions, the fields on all of the other segments. So we can build this matrix of bulk to boundary propagators. So if this delta function on 2 will have a response on 2, a response on 1, and a response in Euclidean. So we can label this by one of the rows of this matrix. So delta ij here means the field that lives on the segment I in response to a delta function which lives on this boundary of segment j. So here, this field on this piece would correspond to delta 2, 2, since it's the response on segment 2 to a delta function on segment 2. And if we computed how this field propagated to the other piece of the Lorentzian, this would be delta 1, 2, and this would be delta E2, and so on. So we can build up this matrix of propagators. It's composed of a retarded piece corresponding to this piece that propagates into the future, an advanced piece into the past, and some coefficients, these matrix of coefficients Cij attached to each of these retarded and advanced mode dependencies. So this is the general form of the bulk boundary propagator matrix. And so the task is now just to fix these coefficients. We fix these coefficients by making sure that the gluing conditions are satisfied between each of these segments and the boundary values are appropriate. So for example, in this case, we want a delta function for the source term at the boundary in segment 2. So this would fix some combination of C1a and Ca and Cr. So this these gluing conditions and the source conditions completely determine all of these constants. So now, if we think about the field that lives on this geometry in response to sources which are set equal to each other, if we set J1 equals J2, this will correspond to this source function JR in that rotated basis, as I mentioned. Then, in fact, after computing all of these coefficients, you find that there's some cancellations, and what you get left with is just purely a retarded response on, for example, segment 1. So if we insert both delta function on segment 1 and the delta function on segment 2, the response in segment 1 is purely built of GR, the retarded mode. So we know that it only propagates into the future. And so what has happened is that each delta function produces a piece of the Klein-Gordon field that propagates around the full geometry. And because of this Euclidean connection and this Lorentzian gluing connection, then it means that these pieces which propagate into the past and around the Euclidean cancel against each other in the case where J1 equals J2. So in other words, the response to J1 and J2 is purely causal. It only propagates forward in time towards the black hole event horizon into the future. There's no support at all of the field in the Euclidean piece. And this is enough to determine that the field must obey ingoing boundary conditions in the Lorentzian. So this is precisely the configuration, this J1 equals J2, which computes the retarded response function. So this is a proof that if you want to compute the retarded response function using real-time holography, it amounts to computing a field which propagates in the following way with no support to the past. And this is equivalent to just working on a single piece of geometry, not this full piecewise geometry, a single piece of geometry with an ingoing boundary condition. So instead of having a boundary value problem, you converted it into, on this full piecewise geometry, it can be converted into a problem which lives only on a single Lorentzian copy of the black hole spacetime with ingoing boundary conditions at the horizon. And this is precisely the Sons-Daranetz prescription. So that's how the derivation works from real-time holography. So now we can consider the same kind of problem, but for 3-point functions.
Sorry, just one confusion. Yes. So I did not understood where was the matching condition did you put in? Like especially because the Euclidean thing you want it to be 0, whereas the Minkowski things were non-zero. So can you just explain? I missed that point.
Yes. So we didn't impose any. Okay. So what we imposed. Okay. Go back. What we're trying to do is solve this problem. So we have this Klein-Gordon equation. We want J1, J2 on these boundaries, and and 0 boundary sources in Euclidean. And then we want to make sure we have a solution in the sense that we have the C1 gluing condition at these dashed lines.
Yeah.
Right. So the propagator, then we do that with, so we solve that problem by using bulk to boundary propagators. So imagine so that's just to say we put a delta function on the boundary and see what the solution is. And so we have a delta function in 2. What is the solution? That can be determined by summing up all the different modes with coefficients, and those coefficients can be fixed by the gluing conditions and the boundary conditions. So the gluing conditions across these dashed lines and the boundary conditions at these colored lines. So once you impose all of those conditions, that fixes completely this matrixCijr andCija.
I see.
So in particular, for retarded response, if you want to generate this retarded 2-point function, what you need to do is set J1 equals to J2. You want to turn off the JA piece. That's just following from the path integral we discussed in section part 2 of the talk from Schwinger-Keldysh. So you just want to have JR only, so that means you set J1 equals J2. So we have equal sources on the green and the blue. And when you impose, so you're summing up a contribution coming from a delta here and a delta here. And when you do that sum, you'll find that these GA modes cancel against each other because of these coefficients.
I see.
So what you're left with is only something which depends on GR. So when you look at the support of this solution, you'll find it only propagates to the future of these insertions. And the thing which used to propagate into the past is now cancelled against each other. So there was a piece which propagated into the past, went through the join, around the Euclidean, and through this other join, and met the other piece which propagated into the past from this insertion, and they cancelled.
I see.
So the full solution with J1 equals J2, we determine from this calculation, or rather bulk determined from this calculation, that there's no support to the past of these insertions, only into the future. And that's equivalent to an ingoing boundary condition on a single copy.
Okay, thank you.
So that's so you could do the computation in this full piecewise geometry, but now we know that if you're interested in this retarded response, it's equivalent to just the computation on a single piece, let's say this Lorentzian piece, with an ingoing boundary condition. And that's obviously much easier to work with. And historically, that's what's been done with Son's dynamics. So for 3-point functions, there's an analogous computation. So for our 3-point functions we're interested in, we'll just take the bulk model of Einstein scalar, and we'll add a lambda phi cubed bulk interaction as a simple model to work with. And we're going to compute this fully retarded 3-point function. So our Klein-Gordon equation is no longer just equals to 0, it has some bulk source terms given by this interaction, so lambda phi squared. So the quadratic source on the right-hand side. So we're going to linearize, we're going to do perturbation theory. Let's say epsilon counts the orders in perturbation theory. So we insert this perturbation ansatz into our bulk equation. And then, of course, we get the equation for the nonlinear piece, the quadratic piece, which we'll call chi. So we have box of chi is given by this source term given by the linear response result, psi, so psi squared. So this is the equation we have to solve in the 3-point function case. The box of this nonlinear response is given by a bulk source term given by psi, where psi is the solution that we computed in the last calculation. So psi is this purely sort of ingoing causal response to sources with J1 equals J2. So you can see we have psi supported in the bulk in these future light cones of these insertions. And so we're going to have sources in the bulk for this chi field on the right-hand side from these blue shaded regions. So we'll solve this bulk equation of motion subject to the condition that there are no sources turned on in the boundary. And we have matching the C1 gluing conditions between these segments, which ensure that we've solved this equation in a piecewise fashion. So to solve this problem, since we have sources in the bulk, we don't have any sources at the boundary, we don't need bulk to boundary propagators, we need bulk to bulk propagators. So now we've moved our delta function from the boundary into the bulk. So this star is denoting our delta function source. And this produces, again, some retarded response and some advanced piece corresponding to the different modes that exist in this space-time. So we just consider both contributions with, again, a matrix of coefficients, and this produces for us a matrix of bulk-to-bulk propagators. So we can have a delta function in this Lorentzian segment, and we can read off the response here, or in the other Lorentzian segment, or in Euclidean. So that would be a single row in this bulk-to-bulk propagator matrix. If we consider the delta function in this Lorentzian, that's another row. And if we consider the delta function in Euclidean, that's another row. And that's this 3 by 3 matrix. So these ij's are 3 by 3. So we have, again, a similar kind of computation, except now our delta function's in the bulk. And we're going to fix these coefficients, CR and CA, in the same way. We want to make sure that this field is appropriately C1 continuous between all of the, across the segments, so that we've solved the bulk equation of motion in a piecewise fashion. So that's this gluing condition, sorry. We want to make sure that the delta function is where we say it is. So no delta function sources in any of the other segments, and there's a delta function source here for this row in the matrix. So that fixes some other relations. And then we want no sources at all for our chi field. So that tells us this, there are no sources on the boundaries on these colored pieces. So that fixes the remaining parts of these coefficient matrices. So this completely fixes all of theseCij's. So this is our bulk-to-bulk propagator. So now to find a solution at the for the nonlinear perturbation, we need to just convolve these bulk-to-bulk propagators with the sources that we have coming from the linear problem. So the linear problem is these Psi1 and Psi2 pieces, which are the same in these blue shaded regions. So we simply convolve our bulk-to-bulk propagators against those regions. So for example, we have sources from Psi1 in segment 1, and so we're going to use delta 1, 1 against Psi1 squared. And then we also have source in the segment 2, Psi2. So we convolve that with delta 1, 2. And this will give us the field in segment 1. So we propagate from 1 to 1 and from 2 to 1. And those are all of the sources we have. And if you insert these relations and insert all the coefficients which you computed by all of these gluing and boundary conditions, what you find again is purely the retarded bulk-to-bulk propagator. So this piece will not depend on the advanced modes, only the retarded modes. So in other words, you find a purely causal response to these background sources, Psi1 and Psi2. Again, there's no Euclidean support for chi, and everything is to the future of these sources in the bulk. And you can show that this is equivalent to a purely ingoing boundary condition in the Lorentzian on segment 1 for the field chi. If it wasn't purely ingoing, you would find that this chi would have support to the past, inconsistent with these results. So in other words, we found something which is very similar to the Son-Starinets prescription. Let me go back a slide. So instead of a linear order, we have this ingoing condition. And now for the nonlinear order, for chi, we also have an ingoing condition based on this requirement that we've set J1 equals to J2. So this is the piece which generates a purely retarded 3-point function, chi, and we can compute it by using ingoing boundary conditions.
Sorry, can you just, I did not, now I don't, what is chi? Can you explain once more? What is epsilon, please, once?
Yes, so we want the 3-point function. Yeah. So we need to compute the, we need to compute the second, so let's say we're generating it from the 1-point, okay, so the 2-point function you can generate from a single variation of the 1-point function with respect to the source.
Yes.
The 3-point function, we need 2 variations of the 1-point function with respect to the source.
That's right.
So we need the quadratic piece of the 1-point function. We need the piece of the 1-point function which is quadratic in the source.
That's right.
So our source comes from this linear response problem. So we have J1 and J2, which produce psi. And then we feed this into the order by order in perturbation theory and amplitude, and we feed this into the equation of motion, this bulk equation of motion, and the J squared contribution, the source squared contribution will be chi. So we'll see that this psi squared through this lambda phi cubed interaction will generate a quadratic contribution in the sources.
Right. Sorry, what was epsilon? Can you just say what was epsilon? Epsilon was
Sorry, epsilon is just yes. So epsilon just tracks. It's a formal parameter which I've set to 1, but it tracks the number of the powers of sources. So here we have. You can think of this as psi as being order j.
Yeah.
And
Okay.
think of chi as being order j squared.
Mm-hmm.
This is the order j squared piece, and so if we compute the vev of phi, the j squared piece will be given by the vev piece of chi, and so we just take second variation of that, and that will be our 3-point function.
Yeah, sorry, what I was getting confused is because you want, because there is a time ordering, right? Like, so what I was getting confused, would you require epsilon square, or you would require at different epsilon? Meaning there is a delta, or there is a commutator involved, right? It's not just a Euclidean 3-point function at some same time, right?
Right. So all of the yes. So the real-time aspects of this computation are completely tracked by this piecewise geometry. So that what we need to do is find this quadratic response on this piecewise geometry, and the fact that we have equal sources on blue and green, so J1 equals J2, means that this variation we take is of the vev here, the average vev between 1 and 2 with respect to we take the variation of chi with respect to JR, which is the J1 equals J2 value.
Mm-hmm.
And that generates everything we need for this real-time response. It gives us the commutator, it gives us the theta function, and that comes from this bulk infilling of this Schwinger-Keldysh contour.
Okay.
So the fact that you only see this causal response when you set J1 equals J2 is showing you that that's the case. So the fact, so in this 2-point function calculation, by setting J1 equals J2, what you see in the bulk is purely causal response. And that's just a manifestation of the fact that when you set J1 equals J2 in this Schwinger-Keldysh path integral, the only thing you can generate are retarded correlation functions.
Okay.
So that we're going to take variations with respect to this JR, and that will generate retarded correlation functions. And that encodes all of the, again, so if we go back to these things, these variations with respect to JR will generate these objects. And it's a bit difficult to see directly, but that follows from this contour ordering. So these commutators, these nested commutators, these theta functions all emerge from this contour ordering. And that contour ordering is guaranteed by this bulk infilling of the Schwinger-Keldysh contour.
Okay. Thank you.
So that's essentially this real-time prescription in action. So it feels very similar to the way I'm presenting it. It feels very similar indeed to a Euclidean computation, but the crucial aspect of it is that we've done this gluing between the Lorentzian and the Euclidean pieces in such a way that we've got a dual of the Schwinger-Keldysh contour, and so these variations with respect to JR produce us precisely these commutators, nested commutators, and the appropriate theta functions. It's all automatic. So we got to these bulk propagators, and we convolved it with sources, and again, the outcome was that maybe it's not that surprising since we're looking at these fully retarded correlation functions, but the outcome was the response is purely causal. And if you analyze this causal response, even at the nonlinear level, it corresponds to an ingoing boundary condition. So these computations I presented were very schematic in the sense that we just needed these coefficients. So these coefficients we computed explicitly, and that's enough to conclude this ingoing condition. But we didn't do these integrals. To do these integrals requires some numerics. So that's what we're going to discuss next. We're going to completely, we're going to actually evaluate these correlation functions. And we're going to use it using the ingoing boundary condition. So we know that the ingoing boundary condition is enough to compute these retarded correlation functions. So that's what we're going to do. We'll take a single copy of the Lorentzian spacetime. So we have these Lorentzian black hole, a Schwarzschild black hole, and we have a future event horizon, and then we're going to have ingoing boundary conditions. This will be both for the linear piece and for the quadratic piece when we do perturbation theory. We're going to work in momentum space. So essentially, we're going to use translation invariance to fix one of these insertion points to 0. And then we just have two remaining coordinates, x1 and x2, for this 3-point function. And then we get to the, then we do the Fourier transform of this, and that's our momentum space 3-point function. It's labeled by 2 momenta. The remaining momentum corresponds to, is fixed by momentum conservation. So, we have these two boundary value problems I mentioned in the previous 2 sections. We have the boundary value problem for the linear response, and we have the boundary value problem for the nonlinear response. And both of these require ingoing boundary conditions, and that computes this causal response, this retarded response. And if you're interested, we're focusing on deltas 5/2 operators in this ADS5 CFT4. So let's talk about singularities. So essentially, we're thinking about these contact diagrams in the bulk. We have 2 momenta. This 3-point function is labeled by 2 momentum. These is essentially the incoming momentum into this diagram. And the outgoing is just the 2 momentum conservation, P1 plus P2. So what we're expecting to find is that we have singularities when any of these momenta are quasi-normal modes. So if we take a quasi-normal mode momentum, which I've denoted by this Gothic P, if we take P1 to be any quasi-normal mode, we expect to find a single pole of our 3-point function. Or this could be also P2, or the combination P1 plus P2. It's also possible to have more than one of these conditions satisfied at once, so we could have an incoming leg and an outgoing leg being quasi-normal mode. And then this would give us a double pole. So this is what we expect, and this is indeed what we find. So let me show you these numerical results for these 3-point functions. So what I'm plotting here is the real part of the momentum space 3-point function. It's a function of 2 momentum, P1 and P2, and I've replaced those by an average and a difference. So P corresponds to the total momentum running through the diagram. So P is P1 plus P2. And S is the difference between the momentum in the incoming legs. So if S is 0, then both momentum are the same. And if S is non-zero, I've just made them asymmetric. So here what I'm plotting is this function in the complex P plane, so real part of P and imaginary part of P, the total momentum through the diagram. And it's some generic value of S, which I picked to be like, I don't know, 1 plus I or something generic. And this is what you find. So you find a bunch of singularities. These are all single poles. So you can verify the single poles numerically by looking at how they approach infinity near these points. And these correspond, these ones labeled by circle, which I've drawn circles over the top. These correspond to momenta where the total momentum in the system, P1 plus P2, corresponds to a quasi-normal mode frequency. So you can see this singularity, this singularity, this singularity, and so on. All the ones labeled by circles correspond to quasi-normal modes excited through this lambda phi cubed bulk interaction. So we're driving the system at some total momentum P1 plus P2, and that's exciting through bulk nonlinearities, quasi-normal modes. And so we see simple poles corresponding to that effect in this sort of characteristic Christmas tree shape, which we're all familiar with from the 2-point function case. So these are not linear response. These are really non-linear response to these interactions, but they appear in the same place.
Sorry, this P is P1 plus P2 simply, this P?
Exactly. So yes, exactly. So this is P1, this is P2. So if I add them together, I think, yes, I get P. So this is the total momentum. So P is like the outgoing momentum, or P1 plus P2.
And you're saying that you get exactly the quasi-normal modes, at least some of them are like the quasi-normal modes.
So some of them are quasi-normal, yes. So if I go to this value of the momentum, which is given by this omega, this momentum for a quasi-normal mode, that means that P1 plus P2 is a quasi-normal mode frequency, which means this outgoing leg is a quasi-normal mode itself. It sits at a quasi-normal mode frequency.
I
So
see.
that's why. So we get these singularities at quasi-normal mode frequencies, which I've indicated by circles, because this outgoing leg takes on a quasi-normal mode value, and then we get a simple pole in this 3-point function. But it's not so it's not a linear response thing. It's obviously that we've driven the system using P1 and P2 such that the total momentum is exciting through lambda phi cubed this quasi-normal mode. So it's like a resonant excitation of the system.
I see. You could have also plotted in complex S plane. That is that you are not considering, or?
We're going to change S in a minute. So we didn't. Yeah, I mean, it's it's a complex. We have two variables and they're both complex, so we didn't really know the best way. This is the best way we thought of to present it. A fixed total momentum, and then fixed difference S, and plotting total momentum. So I'll show you what happens when you vary S, but we don't have a plot in the S plane.
Okay.
So what you can see, okay, so that was the circles. The crosses, these correspond to situations where one of the incoming legs, either P1 or P2, is a quasi-normal mode. So that will depend on S. So you can see, you can show that these crosses will occur at twice the quasi-normal mode frequency, plus or minus S. So these crosses are a pair plus minus S coming from twice this quasi-normal mode frequency. So when S equals 0, that means that these two momenta, P1 and P2, are the same. Then we would just get a singularity at twice the quasi-normal mode frequencies, because that would be both legs being quasi-normal modes incoming. So we'd have, if S was 0, we'd have 2 omega 1, 2 omega 2, and so on. But then S splits them into a pair of simple poles. So by dialing S, we can move these crosses around in this complex P plane. So we can make them collide with other singularities by choosing values for S. So if we set, as I mentioned, if we set S to 0, these two will come together. These will become in the same place in the P plane. And so these will become a double pole. We can also tune S so that it collides with one of these circles. So we can tune this value of S so that 2 omega 1 plus S is equal to omega 2. And then this cross will collide with the circle. And we'll also get double poles. Let's see that.
Actually, I have a very trivial question.
Yes.
So suppose you didn't do this computation, explicit nonlinear computation, could you have guessed this pole structure already or not?
Yeah, I mean, we did, yes. So this slide here, we did guess what would happen based on just taking these momenta and asking when they're equal to quasi-normal frequencies. We thought that would be where we would find singularities, and that's what we found. I mean, it was just a guess, I suppose.
This is simply probably I mean, this pole structure is something they could have guessed anyway. So it's
Yes.
more of the computations.
Yes, you would have guessed these singularities, I think, yes, in advance. And we're seeing indeed that that's what we're finding. We're not finding, I guess one thing is we're not finding any additional singularities. We're only finding these.
Okay, that's what I wanted. There's no additional singularity that comes to this.
Not for 3 points. I think maybe at 4 points there'll be more things, but I'm not sure. We didn't compute 4 points.
So just to follow up on that.
Yes.
Like suppose I'm looking at CFT, though these are all finite temperature CFT, but in CFT generally there is this notion of OP, like OP channel, which is like 3-point function starts wavelength at 2-point function. Are your diagrams, this thing you are saying is basically, that is the expectation that why they should be the 2-point function poles and the 3-point function poles should be that the same?
I don't have yes, I don't know. So I think usually for OPEs, you would think in position space, so right? You would say points coming close, insertions close together in position space. So do you know what that would look like in momentum space?
No, momentum space, it's not very clear, but given your result is that a 2-point function, the poles are exactly like the 2-point function poles, it somehow indicates that kind of thing, right?
Maybe, yes. I don't know. It's a good question. I haven't thought about the implications of OP. But being in Lorentzian and thermal is tricky to, that makes that even trickier to answer.
Okay.
Yeah.
So just one connection. So there was a recent paper where people are trying to understand in de Sitter space, correlation function in de Sitter space. They make this, this connection that whether the Cosima modes are same as the OP coefficient, OP exactly or same or not. So they were doing it in the momentum space, and this thing sounds very maybe related or something. Sorry.
Okay, I wasn't familiar with that work, but yeah, I can. Yeah, thanks for letting me know. I can look at that. All right, any more questions about this slide? So yeah, so what we're doing now is we're going to vary S, and that will vary. This was, we had 2 omega-1 plus minus S, so we're going to move the S around. So if we take S to 0, that's this left panel, and we're just showing half of the diagram. We're just showing positive real P. When S goes to 0, these 2 crosses become the same, become at the same location, and you can show that this is a double pole, an order 2 pole. And this you can verify numerically. And that's the situation where both of these incoming legs are both quasi-normal mode frequencies. This is the other expected singularity. And then you can dial S, which we have done in this right panel, so that one of the crosses collides with one of the circles. So we've done that here. So this is the case where S was set. S will be the difference of omega-2 and twice omega-1. So that's a situation where you have one of the outgoing legs being in quasi-normal mode and one of the incoming legs being in quasi-normal mode. So that's, again, a double pole. And you can verify that numerically it behaves as a double pole.
Ben, can we conclude in like 2-3 minutes? Or
yes, that's fine. Yes. Sorry, yes, I'm running over. Yes, of course. So one could also, in principle, have triple poles where all 3 are quasi-normal modes, and that would require this specific kind of relation between the dispersion relations for these quasi-normal modes. I think it's in principle possible, but it might be model specific as to whether that happens. So in the model we considered, so this bulk ADS5 CFT4 with delta is 5/2, we couldn't find any of these points, but it's not impossible, I would say. I don't know why it would be impossible. Another comment is that if you want retarded functions with stress tensor insertions, so here's TOO in a retarded sense, this would be the generating energy momentum from driving the system with scalars. This you can derive from water densities. You place the water densities, so here's the trace and the diffeomorphism water density, you place it on the Schwinger-Keldysh contour, take appropriate variations, and you can derive these retarded 3-point functions involving stress tensors essentially for free, and you can derive them in terms of 2-point functions of the scalars. I'm going to skip this section. This was a paper we had recently with Michal Heller, Alex Durantis, and Michal Spolinsky, where we looked at momentum space analyticity, but in the interest of time, I'll just skip over that. And let me summarize. So we computed retarded thermal 3-point functions in holography. We looked at scalar 3-point functions, and using water densities, we can compute also this. We showed that this real-time holography prescription for the retarded correlation functions reduces to some ingoing boundary condition, just like Son-Starinets. And these quasi-normal modes, which played an important role in the 2-point function, also play an important role in the analytic structure of 3-point functions as single and double poles. We didn't see any other singularities in these 3-point functions. This shows that the universality of black hole ring down is present in these nonlinear response calculations. Couple of points of outlook. We were interested in these matrix of correlation functions. In this case, for 2-point functions, there was only one independent component. But for 3-point functions in this 3x3 matrix, there are actually 3 independent components. We only computed one of these, so GRAA, this fully retarded version. But there are 2 more, and it would be interesting to sort of try and compute these holographically. It would be less simple to do because it won't be related to a simple ingoing boundary condition. And then try and understand what this means physically and what are the associated fluctuation dissipation theorems. Obvious generalizations are 4-point functions, conserved currents, we just did scalar fields, relationships between the different real-time formalisms, the question of whether real-time holography, in the sense of these mixed signature spacetimes, whether that's a well-posed problem for holography. If you specify these complex time contour boundary conditions, can you always fill it in a way that's deterministic, or is there some ill-posed nature of this problem? So in perturbation theory, we haven't seemed to see any problem so far, but at a fully nonlinear level, let's say you're doing it numerically, is that even possible, since it's a mixture of hyperbolic and elliptic character equations, and it's not obvious. And then finally, we were probing the bulk interactions of quasi-normal modes, and this may be of interest in the case of sort of thinking about flat space black holes and waveform fitting, as I mentioned at the beginning. But yeah, thank you for your attention.
Yeah, thanks, Ben, for this very nice talk. And yeah, it's time for questions. Okay, so let me ask something about the proof of this thing. So, so even if you put some Euclidean sources, right, to prepare non-trivial states, for example, you can put some Euclidean path integral to create some initial non-trivial state.
Yes.
Should it not be? Shouldn't still? I mean, I would say that the retarded correlation function should be always given supported on the light cone, or should be given only by the ingoing condition, right? So you should be able to, that there should not be restricted only to this specific conditions that you have put in, that Euclidean sources vanish.
That's a good question. So you're talking about, say, 2-point functions in a non-equilibrium setting. So for example, let's go back to this contour. Where is it? Here. So you're saying if on this Euclidean piece, I put some sources or insertions which prepare some state, and then I measure 2-point functions in that state. Is that right?
Yes,
I think,
so
yeah, that's not. So then let's say we're doing a scalar field, then your scalar field will see those extra modes you prepared from the Euclidean piece in their equations. And so I'm not sure if then the propagators will be different, and I'm not completely sure if there will be an ingoing boundary condition. Yeah, that's a very good question. The answer is not complete. I mean, it seems, yeah, what you say sounds reasonable. Perhaps it will always be ingoing, but yeah, I wonder if there's some subtleties there, and to do with the interactions between your scalar field and the thing which you've prepared.
So we actually worried about this question in the context of non-equilibrium version of this horizon cap prescription, which we have a paper on. So
yes.
So there actually the J1 is equal to J2 can only come if you put in if you have to take only the analytic solution, which only implies the ingoing mode always. So only in that context you will get J1 is equal to J2 even in or out equilibrium. Of course, it's very non-trivial whether you can actually do the horizon cap away from like equilibrium, and horizon cap doesn't make it explicitly how you're putting the initial conditions.
I see. Yes.
But what we did do is that we implemented the horizon cap prescription in a context where it's in a context like Jordan flow is in the hydrodynamic limit. So when you go to some hydrodynamic limit, you are sort of in, like, say, in a hydrodynamic attractor kind of thing. So you lose initial conditions anyway. So you are anyway have lost initial conditions. In that context, we have been able to answer it. Recently, we have been thinking about this. So in a way, in this horizon cap approach is sort of is automatic, although it's not quite clear how to, whereas here the gluing works much better way. On the other hand, here, I think in this approach, what was not clear to me that this universality of causal response is very well is explicit. Whether when it should be true for any arbitrary initial condition.
It really isn't clear to me. I think it's a very good question. I don't know that anyone has tried to do that in this context. I think people study excited states not in the thermal case, and then people studied thermal response only, I think, in linear response. I think we were the first people to do it in nonlinear in this context. So I think, yeah, that would be something to consider for future work, definitely. I think it would be very interesting to ask to answer that question. Non-equilibrium, 2-point functions in non-equilibrium setting. Yeah, it sounds very difficult to answer that question, actually. But
or
I
I think structurally, if it is always given by the causal by the ingoing mode, that's the question. So actually, Abhi, who is asking you question, was also part of the paper that I was talking about.
Okay,
But
okay.
I actually,
I'll look into that. Yeah.
actually, one more related question here.
Yeah.
So in principle, I can, in the usual Schwinger-Keldysh case, I can start with some off-diagonal density matrix, right? I can, or, you know, like in some basis, for example, I can have, say, I mean, the density matrix is say alpha beta, and it could be off-diagonal in the semi-classical geometry. So in that case, we'll probably need in, and there are two parts like in contour, right? In and in, right?
Yes, right.
And
I see what you're saying. Yes.
So one can also look at more general settings, or how much people have done this kind of general settings.
Yes, I haven't seen anything along those lines. I've only seen, what have I seen? I've seen in-out computations in Scandaris Runneries, which were for you know, with excited states. I think I've only seen in-out, and not in the thermal case, and not for the in-in. I don't think. Yeah, I think in general, it seems that the whole area is needs more study. Like there aren't that many computations, explicit computations, especially for those sorts of interesting questions about excited states. I think it's a fruitful direction, and lots more work to do. That's my feeling.
Yeah, can I ask one more simple question with this? I have a question with this Scandaris construction, which is as follows. So here you are only considering the ingoing solutions, right? And you are considering the C1 functions. Okay, but suppose I have outgoing, they typically have some non-analyticity at the horizon. Okay. And one of the major motivation of this Liu Glorious approach is to jump around the branch cut, not to exactly hit it, but to go past it along some imaginary direction. I think that's how. So when you have this Hawking mode, how do you exactly glue at the horizon? I mean, when the modes are like, they have some branch cuts at the horizon.
This contour never reaches the horizon, so we don't need to worry about that. You only need to go to as far into the future as you have insertions. So No,
I'm talking about the radial direction. You are gluing across you're gluing the two sheets at the horizon, right?
No. So if we think about the Penrose diagram, which I think I have somewhere. Yeah. So let's take this diagram. So this dashed line, this dashed white line here. If I drew that on this Penrose diagram, it would have some finite t. Let's say I'm here, and it would go into the bulk like this. So it'd be some fixed t surface for all r, and so it would not reach. It would not go through the horizon or reach the horizon.
Okay.
Okay, I think I have to wind up now because it is, yeah, so let's thank Ben again. And so it will be good to see you somewhere. And so by the way, Abhik is in Paris now. So maybe you, if you, you can.
Yeah, I think I met you before. I mean, you were in Julian's group, right? I mean, I visited Geneva, so you were there.
Oh,
right?
yeah, I used to be there, yes.
Recording.